Hello, I'm Sam Dare. I'm the Chief Engineer of the Calvin Mars Rover Design Team. I'm so proud of the thousands of hours our team members have put in over the last few months. We have been hard at work over the past 4 months, and our entirely student-led design team started from scratch. We grew to around 25 members. As a rookie team, we were able to design everything about our team from the ground up. We designed a completely flat org chart with 5 subteams: programming, business, science, mechanical, and electrical. We designed a rover we believe will be a top competitor at the 2019 University Rover Challenge.
I'm Case Van Leer, and I'm the mechanical lead. Our suspension system is a unique, innovative design which utilizes 8 independent linkages to improve flexibility and versatility. Our design has been dubbed the Hexapod because of its 6 wheels and independent linkages, which give it a wide-ranging versatility. The wheels are 3D printed from flexible filament. All the components were designed and machined in our engineering building by the members of the mechanical team.
The equipment servicing task and the extreme retrieval and delivery task require an arm with a great deal of dexterity and reach. We designed a fully custom arm with 6 degrees of freedom, including a 360-degree wrist for continuous rotation. The end effector is a 3D printed claw capable of high-precision maneuvers, which will be crucial in order to perform well in these tasks. The arm itself rotates on a custom turret, which allows it to rotate to the nearest 1.5 degrees with very little backlash.
Hello, my name is Fenton Mullen, and I am the electrical lead. Our goal for the electrical system this year was to create a simple yet effective design. Our custom battery pack consists of 70 21700 lithium-ion cells that have a battery supply at 25.9 volts nominal and 50 amp hours. The battery connects to a bus bar which distributes power to all electronics on board. Our motor controllers are Rev Spark Max Pro motor controllers, which are wired to 11 Neo brushless motors, 6 on the drivetrain, and 5 on the arm. All these motors are controlled over CAN bus by an Arduino Mega. The Arduino also connects to our main processor, the Jetson TX2. Our live video feed is sent back through our AV comm system, consisting of a 8-channel 1.2 GHz transmitter and a second 40-channel 5.8 GHz transmitter for redundancy. We're communicating with the rover through a 900 MHz XB Pro. To transmit our data, we use a dipole antenna on our rover and a Yogi antenna at our base station. Our AVCOM uses clover leaf antennas on both ends. We are also utilizing a U-Blox Neo M8N GPS to identify our rover's coordinates.
Hello, I'm Duncan Van Keulen, and I'm the programming lead.
The programming team is tasked with designing, operating, and integrating the individual software subsystems. To keep our design modular, simplistic, and easy to debug, we're using individual Arduino microcontrollers to operate each subsystem. This offloads these tasks from our main computer, a NVIDIA Jetson TX2, which is used for the main hub of our ROS integration, as well as image processing with our Intel RealSense depth camera. Using OpenCV and trained TensorFlow models, we are able to detect and navigate towards a tennis ball in the autonomous mode. Utilizing this, along with Arduinos and our standardized motion systems over CAN bus, we're able to drive autonomously with GPS by means of the RealSense camera and teleoperated using tank drive controls. Similarly, we are able to precisely control the arm utilizing a combination of quadrature and absolute encoders with closed-loop control via PID loops.
Hi, I'm Haley Boss, and I'm the science lead. The science assay this year is split up into 3 distinct analysis sections. First, the environmental analysis. We plan to use a temperature probe, a moisture probe, and a pH probe. These 3 probes will establish base evidence that will determine the likelihood of life existing in the sample location. The second part requires the analysis of the geological structures, and this will be done using an imaging microscope. Specific minerals that we will be looking for include apatite and calcite, as well as looking for microfossils. The third technique is Raman spectroscopy, and this will help us get a better understanding of the chemicals present in the sample. We are specifically looking for sp2 hybridized carbons that will lead us to conclude the presence of active natural chemical synthesis.